Electricity is often mistaken for magic, but it is actually the controlled movement of microscopic subatomic particles. These tiny, fundamental building blocks of matter are known as electrons, existing within every conductive material. Within conductive metals like copper, these electrons are loosely bound and capable of hopping between atoms. This constant, microscopic motion creates the potential for energy transfer that powers our entire modern world. However, to create a truly functional flow, these particles require a consistent external push from outside. We define this essential driving force as voltage, the fundamental pressure that initiates all electrical movement. Much like water pressure surging through a pipe, voltage provides the necessary force to drive electrons. It pushes the particles through a circuit, overcoming the inherent inertia that keeps them otherwise stagnant. Without this critical pressure, the particles remain entirely motionless, trapped within the lattice of the metal. Once the push is applied, we measure the resulting flow rate as current, expressed in amperes. This current represents the volume of electrons passing a specific point within the conductive wire path. Simultaneously, resistance acts as the primary traffic control that actively opposes this rapid energetic particle movement. Insulators like rubber or plastic provide high resistance, effectively blocking the path of the flowing electrons. These materials prevent the current from escaping, ensuring that electricity stays exactly where we need it. Conversely, resistors in a circuit can intentionally slow down the flow to manage the total energy. They convert electrical energy into useful outputs, such as heat for a toaster or bright illumination. This transformation of energy is the core mechanism that allows us to utilize electricity for tasks. The interplay between voltage, current, and resistance forms the bedrock of our complex, modern technological world. Every device we use relies on this delicate balance of forces to function with perfect precision. By manipulating these variables, engineers can direct the flow of electrons to perform highly specific work. It is a masterclass in physics, turning invisible subatomic motion into the light of our homes. The movement of electrons is not chaotic, but rather a highly ordered and strictly controlled process. Each electron contributes to the collective flow, creating the current that powers our vast global infrastructure. Copper wires serve as the highways for these particles, guiding them toward their intended destination points. The atomic structure of these metals allows for the efficient transfer of energy across long distances. Understanding this movement is the first step toward mastering the invisible forces that surround us daily. We observe the effects of this energy, yet the microscopic dance remains hidden from our view. Voltage acts as the catalyst, turning potential energy into the kinetic energy of moving charged particles. Current measures the intensity of this activity, reflecting the sheer volume of electrons in the loop. Resistance ensures that we do not have too much of a good thing, protecting our devices. It is a system of checks and balances that keeps our electrical systems safe and functional. From the smallest battery to the largest power plant, these principles remain constant and entirely universal. The physics of electricity is a testament to human ingenuity and our ability to harness nature. We have learned to tame the electron, directing its path to serve our many complex needs. This controlled movement is the heartbeat of our civilization, pulsing through the walls of every building. Without this understanding, we would be left in the dark, unable to harness such powerful energy. The study of these particles reveals the intricate design of the universe at its smallest scale. Every light bulb that glows is a result of this precise orchestration of voltage and current flow. We continue to refine our control, making our systems more efficient and capable than ever before. The journey of an electron is a story of energy, transformation, and the power of physics. As we delve deeper into the circuit, we see how these components work in perfect harmony. The battery provides the initial surge, a reservoir of potential waiting to be released on command. The wires act as the conduits, ensuring that the energy reaches its destination without significant loss. The load, whether a motor or a screen, consumes this energy to perform its specific function. The switch acts as the final arbiter, deciding when the circuit is active or safely dormant. This simple loop is the foundation upon which all our modern electronics are built and maintained. Even the most complex supercomputer is essentially a massive collection of these basic, fundamental circuit loops. We observe the electrons moving, yet we never see them individually, only their collective, powerful effect. The flow is constant, reliable, and essential for the functioning of our interconnected digital global society. Engineers spend their lives perfecting these pathways, ensuring that every electron finds its intended target path. We are surrounded by these invisible currents hidden behind walls and inside our small handheld devices. The mastery of electricity represents one of the greatest technological achievements in all of human history. Every time we charge a phone, we are participating in this grand, invisible, and fascinating dance. The electrons move, the energy transfers, and our world lights up with the power of physics. It is a process that repeats millions of times every single second, keeping our civilization moving. We rely on this steady stream of energy to power our homes, our industries, and our lives. The science is clear, the principles are sound, and the application is truly transformative for everyone. As we continue to innovate, we find new ways to harness this incredible, invisible, and powerful force. The future of technology depends on our continued ability to direct these tiny, energetic, subatomic particles. Electricity is the silent engine of our world, driving progress through the simple, elegant flow of electrons. Building upon this foundation, electrons must travel through a continuous, unbroken path known as an electrical circuit. This essential loop requires 4 specific components: a power source, a conductor, a load, and a switch. When the switch is closed, the loop is complete, allowing electrons to flow and power our devices. Engineers manage complex systems like home wiring using parallel circuits, which provide multiple branches for electricity flow. These parallel branches ensure that if one appliance fails, the rest of the system remains fully operational. This design stands in stark contrast to series circuits, where components are linked in a single line. In a series circuit, a single break in the path stops the entire flow of electrical current. From the atomic dance of electrons to the massive grids powering our cities, electricity is a masterclass. It is a masterclass in controlled particle physics, demonstrating the incredible potential of these tiny subatomic particles. By understanding these fundamental loops of open and closed paths, we gain a much deeper appreciation. We appreciate the invisible currents that sustain our daily lives and drive our technological innovation forward today. The mastery of these circuits remains the cornerstone of our modern, electrified, and highly interconnected global society.